Welcome back to Biz 230 Introduction to Business Statistics, or Applied Statistics is another way to think about this. In this video, what we're going to be taking a look at is Chebyshevs Theorem and an example to work through it. Now, historically, this is the most problematic part of the course as we get into the beginning bits of descriptive statistics and distribution theory, and that's primarily because we're really changing gears. Up until this point, we've just been, hey, calculate the mean, calculate the median, calculate the standard deviation, and it's all been just, here's a formula, throw numbers into it, get an answer. Here is Chebyshevs theorem, we get a little bit more abstract, we begin to take a look at actual distribution theory itself, and as a result, we're kind of tying together threads from everything we've looked at so far. So let's go jump over, let's take a look at our example, and let's hopefully try to tie this together in a bit more of a clear way. So to start us off, what we have is we just have our distribution, our random variable underneath consideration. We have x. And we see that x runs from 19 all the way to 44, such that we have 19 observations altogether. Now we'll presume that this is a population, and we see that with that we've already calculated our population mean of 30 and our population standard deviation of 7. Right, this was just done as a convenience. Of course, we could have calculated this ourselves from the raw data using our formulas. Similarly, what we've already done is we've set up our bins. So again, using our rule of 2 to the k and our bin width formula, we have taken our raw data, we've categorized it into bins, and we've created for ourselves a histogram. And so we have our histogram, that is our distribution of the data, such that we have, hey, our frequencies within all the different amounts, right? So the relative frequencies there, going from, I know a bit of chicken scratch there, 40%, 30, 20%, 10%, right? And we see, okay, our distribution kind of looks as such. Kind of up, down, then we got this big bulk of observations right near the max side again as well. Okay, so what we can always do with this, right, and what we've done before is we've said, hey, okay, what percentage, what proportion of observations are going to be less than 25? And right, we can do that. We can just go, okay, what proportion is less than 25? Okay, there's 25. What proportion is less than? We can just say, hey, that's these two boxes here, right? These two boxes are going to be less than 25. And hey, those two boxes are 10.5% and 10.5%. So we could say quite readily, hey, the probability that x is less than 25 is going to be equal to 0.21. Right? There's a 21% chance that we're less than 25. Okay, great, that's nice, that's good to know. But what if we don't actually have this kind of information? What if we don't have this kind of detailed breakdown? What if instead I wanted to say, okay, hey, I know that my mean is 30, and I know that a standard deviation is 7, so let's just visualize this. I know my mean is right here at 30. Okay, that's the value of my mean. We can write that down. That is mu, our population mean, and that is mu of x, right, our random variable of interest. I then know that my standard deviation is 7. So that is, I know that, hey, the typical observation, the typical amount that any one value of x will deviate, right, one value of x will deviate from this mean is going to be 7 units. So that is, I should expect most of my observations to be within plus or minus 1 standard deviation. So what's that going to be? 30 plus 7 is going to give me 37 on that side. Write that down. 37, that's plus 1 standard deviation. Or on the other side, 30 minus 7, that's going to be about 23. 23, that's minus 1 standard deviation. We could bring this farther. We could go, hey, how many are going to be within plus or minus 2 standard deviations? So, okay, plus or minus 2 standard deviations. Let's just change colors for that. We'll go to green. So in that case there, okay, 37, and then another 7, right, another standard deviation. So 37 and 7 is going to give me 44. There we go. So that is within 2 standard deviations of my mean of 30. Or going the other way, 23 minus 7, what is that going to give us? 23 minus 7 is, of course, 16. So 16 is going to again fall right about there. And I get 16, which is minus 2 standard deviations. Okay, so what if instead, right, the first case we just said, hey, what's the probability that, hey, one of these values is less than 25? So let's change colors again. And, right, realizing that, hey, 30 minus 7 gave us 23. For 30 minus 14, 14 being 2 standard deviations, gave us 16. Well, hey, if 1 standard deviation is equal to 7, well, we could go, hey, half a standard deviation is going to be equal to 3.5, right? If a full standard deviation is 7, well, then half a standard deviation is going to be 3.5. In the same kind of way, I can say 1.5 standard deviations is going to be equal to, well, okay, 1 standard deviation is 7, half a standard deviation is 3.5, so 1.5 standard deviations is going to be 10.5. So, okay, there we go. We have 1.5 standard deviation is going to be 10.5. So let's take a look at that. Let's just make some room here. Let's get rid of this green line. There we go. And we can take a look and we can say, okay, plus 1.5 standard deviations. So, okay, my mean is 30. I'm going to go up 1 and then half of 1. That's going to give me 40.5. We'll go 40.5 there. That was plus 1. Let's make that a little bit more room, sorry. Plus 1.5 standard deviations. And again, that's a 4. We're looking at 40 there. Okay. Very similarly, we could go down. We could go, okay, minus 1.5 is going to give us right about there. That's going to be 19.5, right? That's 30 minus my 1.5 standard deviation. So 30 minus 10.5 will give me 19.5, which is minus 1.5 standard deviations. Okay. What if we wanted to figure out the proportion of observations that is going to fall within plus or minus 1.5? Oh, that's a funny looking 5. Let's try that again. 1.5 standard deviations of the mean. Well, again, just like before, we actually have the tools that we can just go and calculate this. So here, let's get rid of all of our red dots so we can actually calculate that. And in this case here, because we have the data, we can just go through and say, okay, we're interested between values bigger than 19.5, less than 40.5. So we're looking at, hey, what is the probability that 19.5 is less than x, which is less than 40.5? That is, again, to put it a different way, probability that we are between negative 1.5 standard deviations less than x, which is less than plus 1.5. That's a plus, sorry, standard deviations. Okay, just going to go count that then. Bigger than 19.5, so that's going to be 1, 2, 3, 4, 5, 6, 7, 8. Less than 40.5, so okay, we're at 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, in this case here, we have 16 out of 19 observations that fall within this range. So, okay, 16 out of 19, what does that give us? Well, 16 out of 19, that gives us something like 0.842. 0.842. That is, right, that is another way to put that. That's our decimal form. We could say 84.2% of observations fall within 1.5 standard deviations. Great. Awesome, right? We can just calculate that. We can just work that out. Easy counting, and we have our area, right? To think about this area, we've just calculated all of this here, right? Everything between these two blue dots, we've just said, okay, what is the area underneath our histogram between these points? And that's given us our probability. 84.2% of observations fell within 1.5 standard deviations. Great. What if, and hear me out, what if we have a situation where all we know is this? That is, all we know is the mean. All we know is the standard deviation. We don't have these values of x. We don't have this frequency table. We don't actually have the histogram. That is, all we have, let's just scroll down and do that again. All we have is this statement that mu equals 30 and that our standard deviation is equal to 7. That's it. Now, okay, we know that's because it comes from this, but right now we don't. Right now, all we have is this information. The rest of it is hidden, it is gone, it is out of our reach. And we still want to answer the same kind of question. We still want to answer, hey, what is the probability that we have a value between 19.5 and 40.5? That is, what proportion of observations will fall between 19.5 and 40.5? What proportion will fall within 1.5 standard deviations of the mean? So, okay, we have our number line here. We have x. We know that it has a mean of 30. We know that we could go 37, 44, and then going the other way, we could go 23 and 16. Right, again, where did these numbers come from? Well, that was the mean. That was plus 1 standard deviation, plus 2 standard deviations, minus 1 standard deviation, and minus 2 standard deviations, right? That's just what we had up here. Let's go take a look again. Right there, mean, minus 1, minus 2, 23, 16, plus 1, plus 2, 37, 44. 16, 23, 37, 44. The only difference is we're just saying we don't know what the bars look like. We don't know what the histogram looks like. We don't know what the distribution looks like. But we still have the same question. We still want to know, hey, what is the likelihood that I have? What is the proportion of observations that fall between these two lines? That is between 19.5, 40.5. So, okay, again, on the other side of that, that is minus 1.5 standard deviations. On the other one, plus 1.5 standard deviations. What is going to be the proportion of observations that fit in here? And okay, keep in mind, we know the answer. We know the answer to be 84.2. In this scenario, it seems like maybe we can't do it. All we have is this mean, all we have is a standard deviation, and I don't know, right? Where does our data fall? I know that, okay, plus or minus 2 standard deviations. I know 1 standard. Ooh, I don't have enough information. This is where Chebyshevs theorem comes to help us. So, for k greater than 1, Chebyshevs theorem, just quite simply mathematically, 1 minus 1 over k squared gives us the minimum proportion of observations that will fall in k standard deviations. So, okay, what is the guaranteed minimum proportion of observations that are going to fall within k standard deviations? In this case here, we are interested in the proportion that would be within 1.5 standard deviations, plus 1.5, minus 1.5. So that is, we're interested in a case such that k equals 1.5. And we want to figure out, hey, at minimum, what can we be guaranteed will be the number of observations in between these 2 points? Okay, throw that into our equation. 1 minus 1 over 1.5 squared, and that's going to yield for us, well, let's go 1 over 1.5 squared first, 1 minus that answer there, and we are going to get 0.5555 repeating, so we're going to go 0.556, or 55.6%. Okay. And you might be looking at this and you might be going, okay, wait. We just said, hey, we had 84.2% of observations within plus or minus 1. How come now we're saying, 84.2% within plus or minus 1.5 standard deviations, right? Between this 9.5 and this 40.5. How come we've gone from 84.2% down to 55.6% within this same range? Well, again, that is the difference between being able to deal with the actual data and get an actual guaranteed result and dealing with Chebyshevs theorem. With Chebyshevs theorem, all this is giving us is saying, hey, we have no idea what this distribution looks like at all. No idea. It could look like anything. As a result, we can't be 100% certain as to what proportion falls within these bands. Instead, what we can be certain of is the minimum percentage that will fall within these bands, and that is we can be guaranteed that at least 55.6 will fall within 1.5 standard deviation. That is, at least 55.6% of observations will be between 19.5 and 40.5. The thing is, it may be more. It may be more of our observations that fall, as we see, right? We see that it was actually 84.2. So in this sense, Chebyshevs theorem is a bit of a weak theorem. It just kind of gives us that minimum proportion of observations that fall within the band. But it's still a very powerful theorem in that it at least gives us something. For only having a mean and a standard deviation, it gives us some information about the distribution, and it gives us some information about, hey, the minimum percentage that are going to fall within that band. This is often useful in business. This is often useful in lots of situations where all you have is the mean and the standard deviation, and you want to figure out, okay, what is going to be the minimum proportion that are going to support X, Y, Z? Or what is going to be the minimum proportion of products that have some kind of defect? What is going to be the minimum proportion of prices that are going to fall between this minimum price and this maximum price? Right? How many products are going to be sold within that price? So very useful in that, in the sense that it gives you that minimum band, that minimum boundary as to the number of observations. Hopefully this helps a little bit with Chebyshevs theorem. As we go on through the course, we do get more and more into the distributions and more into figuring out these proportions underneath the distributions. So it is important in that sense, but the abstraction of just this unknown ethereal distribution disappears, because as we move forward, of course, we are dealing with known distributions, and it allows us to do situations like this, where we just get, hey, how many are between 19.5 and 40.5, and we just can figure that out quite easily, versus this ethereal unknown distribution and having to figure out a minimum. If you have any other questions about this, please feel free to let me know. You can shoot me an email, you can post on the D2L Frequently Asked Questions page, or of course, you can comment below. Thanks.